Good morning, everyone. Welcome. Welcome back. It's interesting that it's Tuesday, and even though we saw each other yesterday, it sort of feels like the beginning of the week because we didn't really get a chance to meet as a class. And the assessments, while certainly interesting and providing a great opportunity to have a one-on-one conversation, aren't exactly the most casual of meeting hangout places. So it's good to be back in class, to be having this chance to kind of recap where we are at, and then also the opportunity to look at some new material that's actually pretty cool. When last we saw our intrepid heroes were working on applications of double and triple integrals. They were finding the mass of lamina of solids, and then the centroid or center of mass of laminas and solids. And that was all very nice. It's lots of calculations, but it shouldn't be that difficult conceptually. It just requires a little bit of practice and remembering a few basic formulas. Today we're going to shift gears a little bit, and I want to start by reminding you of something that you did a long time ago. So way back in Calculus 2, you learned about a whole bunch of integration techniques. And you may have noticed that we haven't, for the most part, done any or spent any time on integration techniques. So the most basic integration technique you learned in Calculus 2 was calc by substitution. And what we're going to do here today and tomorrow is analogous to that integration by substitution. Basically, this is going to be a multivariate or multivariable change of variables. And it's going to introduce this new little thing called the Jacobian, which is the fancier or more precise name for the thing previously we've been calling the scaling factor. So in the last section last couple of sections, we talked about that scaling factor. That all kind of comes home here in this section, 16.7, on multivariate change of variables and the Jacobian. So let me begin with an example that I hope is somewhat familiar to you. Perhaps not in a good way. This question probably looks a little bit familiar to you. I think I need to share the screen. Ooh, actually I'm ahead of myself. I'm a little ahead of myself. I'm getting a little too excited.
Dusty, what section is this?
This is 16.7 on the change of variables. Okay, I got too excited about where we were going. So we're going to talk about a change of variables in a single variable, the old school stuff, how this could have helped us. We're going to gloss over the theory. It's here just for completion's sake, and then we're going to work some more examples. So let me just start by reminding you of things we've done in the past. So suppose you have the integral from a to b of sine 2x dx. Now, at this stage of your math career, you could probably find this antiderivative and evaluate it without writing very much. But in the old days, or previously, you would do the substitution and you let u equal the 2x, du equals 2 dx, and your new integral after the substitution would be the integral from 2a to 2b of sine u times 1/2 du. And I want to point out the fact that when we did this, the limits of integration changed, the integration changed, and we introduced the scaling factor 2, or 1/2. You might say, well, which is it? Is the integration, or is the scaling factor 2, or is the scaling factor 1/2? Yes. And you can think about it as follows. This length in sine 2x would be a length of pi over 2. The length in sine x would be, of one bump, would be pi. And if we went this direction, you could think about as that we've scaled up. You could scale up by 2. By 2 times. Or if you prefer, you could go the other direction, and you could think about it as you're going to scale down by 1/2 time. Make sense? Questions about this? Very good. So the main point is that substitution requires changing the integrand, that's this part, the limits of integration here, and the introduction of a scaling factor, all 3. And so let's start where I got a little bit ahead of myself, but let's start by looking at where this might have helped you on your last assessment. So you may remember this question right here, where we wanted to find a triple integral to compute the volume of the wedge of the square column, absolute value x plus absolute value y equals 10, created by the plane y equals 10 and x plus y plus z equals 10. And so we sketched kind of this solid here, and I'm hoping you all spent enough time on your homework to recognize that the base of the solid looks like this diamond over here on the right. Which is what I've drawn here. For those of you that worked all the way through this, which I'm hoping is everyone, you realize that in order to integrate over this region, you ended up having to split up your integral into 2 parts. And so you had a triple integral to find the volume above this region and another triple integral to find the volume in the second region. So you were adding 2 triple integrals. And that was really, really frustrating, especially so because if you're anything like me, you're probably thinking to yourself, gee, if I could just, somehow rotate this thing so it was straight up and down, this would be so much easier. But we didn't know how at that point. So here's the plan. We are going to do a substitution, just like we did in the past. So we're going to let, I'm going to try to match my notes. We're going to let u equal x plus y, and we're going to let v equal y minus x. And so this turns that top equation, this turns our various bounds into, becomes, let's see, it's going to become blue u equal to 10 and u equals negative 10. And then v equals 10 and v equals negative 10. And then the plane below is still z equals 0. And the plane above would be, if I solve for z, I would have z equals 10 minus u. Let me highlight. Questions so far?
Are we going to see an example where like it's maybe not symmetrical?
Yes, but most of the examples we're going to work with are actually pretty straightforward. Yeah. Yeah. So that we have some examples that are, yeah. Okay. So let's see what we can do with this. So we can set up the integral. We can say that our volume is now equal to the triple integral, and our z values are still going from z equals 0 to z equals, it was 10 minus x minus y, so, but now it's just going to be 10 minus u. And then that's our dz. And then maybe our u values are going to go from u equals negative 10 to u equals 10. And our v values are going to go from negative 10 to 10. And what part of substitution have we not accounted for? There's one thing, thinking back to Calc 2, that we skipped over. Go ahead, Damon.
The scaling factor?
Exactly. So we skipped over this scaling factor. Exactly. Okay. So let's spend a little bit of time on that scaling factor. And at this stage, I'm just going to deal with that scaling factor geometrically. So let's think about it in terms of xy for a second. So in terms of xy, the region looked something like this. And you may recall that all the vertices were at 10s or negative 10s. So if you focus in on just one triangle here, what are the two lengths that we know? I think we know that the base is 10, the height is 10. So what's going to be the hypotenuse of this triangle?
Use Pythagoras.
Can you say that again?
Square root of 200.
Square root of 200. So it'd be 10 squared plus 10 squared all under the radical. Square root of 200, which would be the same as 10 root 2. So this is square root of 200.
Yep.
And so now if we wanted to find the total area, and there isn't a great notation for this. So I'm going to call this the area xy, like the xy area. That would be 10 root 2 times 10 root 2, or 200. Okay.
Why did we do two of them?
I did two of them because I'm now trying to find the area of the whole square. I don't know what I'm boxing in. Does that make sense? So that's if we're working with xy. What if we're working with uv? So if we're in the uv world, we're going to go from minus 10 to 10, minus 10 to 10. Oops, that's negative. Something along these lines. And I don't think we have to do any complicated Pythagorean identities here. What's going to be our area in the UV world?
400.
A nice 400. So what's the scaling factor between the two worlds? Sort of depends on which direction you're going.
Sure.
Right? We double if we go one direction, we half if we go the other direction, right?
Right.
So in this particular case, me see if I can get the colors to work for me. So we're trying to find this scaling factor. So in our case, where are we ending up? Are we ending up in an XY world, or are we ending up in a
UV? In a UV.
UV.
We're ending up in a UV world where the area is 400, right?
The scaling factor will be half.
Yeah.
Exactly, but we started with XY, so we got to keep everything equal. So our scaling factor is going to be, in this case, the area XY over the area UV, which would be 1/2. Yeah. Questions about how we got here? Very good. So let's put it all together and see how this works. See if we get the same answer as before. So our volume is going to be the integral from -10 to 10, -10 to 10, 0 to 10 minus u of 1 times 1/2. Where'd that half come from?
Scaling factor.
Yeah, this is that scaling factor. Okay. So let's just crunch through our integral and see what happens. So notice here's one line. So there's no v's anywhere in sight. So we should be able to just pull out the width of this interval, which is 10 minus minus 10, or 20. The scaling factor is 1/2, so I can pull out the 1/2. And then antiderivative with respect to z would be z, evaluate at 10 minus u and 0 will just give us a 10 minus u. So here's the stuff from the v's, here's the scaling factor, here's our antiderivative already evaluated for the inside integral. So this is 10 times 10u minus u squared over 2 from -10 to 10, which would be 10 times 100 minus 50 minus 100 minus 50 again, minus 50 plus 50 or 200. Oh, with an extra 0, 2,000, the other 200. Which I think is a lot easier than what y'all had to do over the weekend.
Yeah, that was really nice.
Yeah, and maybe I was the only one, but I'm guessing many of you saw that original question and looked at that region and were like, I can see it's a square, I just don't know how to take advantage of that symmetry. And so we had to ended up having to break it up, and it was aggravating. And so you see that we can use this simple idea of a change of variables as long as we account for that scaling factor, and it can be pretty practical right off the bat. Are there any questions about what we've done so far?
So did we make our scaling factor a 1/2 because we used the dz, du, dv limits? Or those variables for integration? Is that where we made it 1/2 instead of ×2?
We made it 1/2 because we were going from a world that had where the area was 200 to a place where the area was 400, and we had to, since the area was doubling, we had to kind of like undo that doubling. And so the 1/2 basically undoes the change in size of the area.
Okay.
Does that
Yeah,
make
that
sense?
makes sense. Yeah. Thank you.
It's not always going to be quite this easy, but frankly, oftentimes it will be. Cool. All right. Let me go back to a simple statement. When you do a substitution, it changes 3 things. It changes the limits, it changes the integrand, and it also introduces the scaling factor. In order for this to, this one down, the bottom one here, this just sort of happens. It's like an afterward, like it's a result almost. But in order for this to work, the substitution has to really help in both of these areas. Helps or fits. So you could do a substitution that only helped the limits, but if it didn't help the integrand, that would not be a good, it wouldn't really help make your life that much better. It could just help the integrand, but not the limits. Not gonna really make a difference. In all the examples you'll see, basically the substitution is going to impact positively the limits and the integrand. And that's kind of your clue that this multivariate change of variables will be helpful to you. Let's do another example. So this is example 2 in the notes. So I want to find the double integral of sine 9x squared plus 4y squared dA, where d is in the first quadrant, and it's the region that's bounded by 9x squared plus 4y squared equals 1. Do you remember what this shape is? I mean, it's solid, but do you remember what that shape is? Anyone?
Quarter circle?
Not quite, but it's similar.
Ellipse?
It's an ellipse. An ellipse. And an ellipse is just a messed up, what was that, Croy?
Yeah,
Messed up
it's like a
circle.
stretched circle.
Yeah, this is like a messed up circle. And you're like, this could be so easy. And yet suddenly it becomes difficult because we have a messed up circle. And so what might be a good substitution here? Like this is a messed up circle, so let's make it a circle. What kind of substitution can we do to make this a circle?
U is equal to x squared plus y squared?
We need to break. So if it was a circle, what would it look like?
X squared plus y squared equals 1? Or some sort of radius equals...
Something like that. Something like u squared plus v squared equals 1. If we want to end up at u squared plus v squared equals 1, what do we need our u to be?
3x.
9x.
3x.
No, yeah, 3x.
So 3x times 3x would be the 9x squared. And our v?
2y.
2y.
2y. And so now that integral will be the double integral over, the integrand is going to become sine of u squared plus v squared, like that. That part looks good. The limits of integration are going to become I'm going to just draw it. It's the unit disk. Sorry, just a little bit. And we have some sort of a dA, but now it's a dA prime because it's got u's and v's instead of x's and y's. What are we missing? What's the one thing that we're missing here?
Scaling factor.
Scaling.
We're missing, exactly, that right here, boom, we need to have that scaling factor. And we could probably go through and compare the areas of ellipses and circles, but at this point, we're just going to set things up and leave a space for that scaling factor, and later we'll come back and fill it in. Let's just do one more line on this question. Yeah, let's just do one more line so that you can see how, well, no, we're not. Once we get it to this stage, how are we going to actually integrate this? What would be the next step? We would convert this to...
Try the new label.
Cylindrical?
Not cylindrical.
Spherical.
Not spherical. Third time's a charm.
Polar?
To polar. We're going to convert this to polar coordinates. It's a double integral. So since it's a double, our options are rectangular and polar. If it was a triple, then our options would be rectangular, cylindrical, and spherical. So it's a double. So we're going to try to switch this thing to polar coordinates, but that'll actually happen tomorrow. We're not going to worry about that today.
Could you say that just one more time, just so I can remember? You said like if we're in 2 dimensions, we want to do polar?
You have rectangular and you have polar. If you have triples, you have rectangular, you have cylindrical, and you have spherical. That work?
That's it. Thank you.
Cool. Let me put you into breakout rooms for just a couple of minutes before I want to do a couple more examples if we can, but I'd like to make sure that you're tracking with this main concept. So let me do that. So just for a couple minutes, just check in and see if everybody's understanding why we're doing the change of variables and how the change of variables is working. We haven't talked yet really about how to find the scaling factor, so you don't need to focus on where it's coming from. Are there any questions about this before we do another example?
Yeah, I'm still a little confused what scaling factor specifically is.
So we're going to talk a little bit more like how to find it or what it represents.
Both.
Both. Tomorrow we're going to talk about how to find it. So I'm going to set that one aside for the time being. In terms of what it is, it's analogous to that differential part when you were doing substitution. So we had the integral of sine 2x dx, and you let u equal 2x, and you ended up with this du equals 2 dx. This 2, that's your scaling factor. And it's basically the relationship between the x coordinates, like what happens in x coordinates and u coordinates. Maybe a place that would be more familiar is, think about, you have feet and you have meters.
Yeah, I
Right.
understand now.
And so it's just the conversion between different sets of units.
All right, cool.
Good question. Any other questions? Very good. So I think, or I hope, that you can look at this example 3 and start to see some of the pattern. You see that the integrand seems to match really nicely the bounds of this parallelogram that enclose our region D. And so we might notice that numerator matches these guys, denominator matches those. And so what would be a good substitution?
Let u equal x minus 2y.
Sure. And v might be
3x,
minus y. Good. And so then this integral I might be the integral of the u over the v. And I don't know which order we want to do. Maybe we can leave some space. Maybe we'll do dv du. What are our v's going to vary between?
1 and 8.
1 and 8. And our u's between 0 and 4. And what is it that we can't forget?
Scaling factor.
Scaling factor. We don't know how to find it yet, but we know there's going to be one. Even if that scaling factor turned out to be a 1, there's a scaling factor. Good. See how it happens there? Let me do one more example. No more difficult. Well, maybe just a teensy bit more difficult. Here we've got a slightly uglier integrand, and we have an x plus y, and up above in the exponent you see an x squared minus y squared. What would be a convenient way of writing x squared minus y squared?
X plus y quantity times x minus y quantity.
Happy factoring. Thank you, Robert. And now suddenly you see the x plus y showing up in a whole bunch of places, and you see the x minus y showing up in a few places as well. So what do you want to let your u be?
X plus y.
X plus y. V can be x minus y. And now your integral can be the double integral of, looks like it's u e to the uv. And then we got to leave some space. And then, I don't know, which one do you want first? Maybe dv du, I don't know. We'll figure that out later. Our v's are going to range between 0 and 2, 0 to 3. What goes in the parentheses?
Scaling factor.
Scaling factor. Okay. So you can see from those 3 examples, they were all pretty fast. You can see from those examples that this change of variables can be pretty straightforward, just like it was in Calc 2. It's not that difficult to implement, and it tends to make things really nice, especially if it's set up that way. But there's still a hole in our knowledge. We understand that there needs to be a scaling factor. We just don't know what it is, and we don't know how to find it. So when we pick this up tomorrow, we will spend a good chunk of our time on figuring out what that scaling factor is, how to find it, and actually finishing out some of these questions. So in conclusion, in a time when we are substituting throughout our lives, right? We're trying to figure out how to make do in the COVID crisis. May you smoothly navigate these variables and enjoy your studies to the outermost limits. Thanks, everyone. Feel free to hang around if you have questions, but I look forward to seeing all of you tomorrow.